Hi, I'm Gary Bistiak. Today I'm going to present my project, an FPGA-based synchronous motor drive. It was done as the final project in digital systems implementation for the Department of Electrical and Computer Engineering at the University of Manitoba in Winnipeg, Manitoba, Canada. First, we'll power up the system. And then we can launch the user interface that controls the motor drive. And we're presented with a command line interface. There are some basic built-in commands like read, write, block read. My favorite command is GUI. So this is the main interface to the motor drive. Let's look at the open loop first. We'll set the modulation index to 1.0. Set our frequency to 2 Hertz and change a couple of the settings here. So you can see at the bottom there, you can see the PWM switching command being sent to the switches. There is no voltage appearing right now because I haven't turned the main power on. This is a torque command. I'll explain that a little bit later. If we raise the frequency, we'll actually be able to see about half a period of the PWM waveform. From here we can look at the plotting facility, we can capture results. Right now there isn't going to be too much to look at except for the modulating waveform. And we can zoom in on that, and as we expect, it's a sine wave because we're doing SPWM. Alright, if we change the frequency, so we can close that, we can slow that down to say 20 Hertz. Do another capture. Alright, and we can take a look again at the modulating waveform, and of course the frequency has changed. Recall we had to zoom in quite a bit last time. And there's the sinusoidal waveform again. If we go back to 2 Hertz, you'll actually be able to see it. There are 6 LEDs on the lower left of the board. Those are actually connected to this modulation index, or sorry, to the modulating signals for phase A, B, and C. And you can actually see by the brightness of the LEDs the modulating waveforms. Alright, let's turn the system power on. But first let's change the modulation index to 0. And then we're going to turn the motor power on. So now the DC bus is on. So now you can see that some waveforms are actually starting to appear here on the voltage, and we should get current waveforms now. So let's go ahead and set our frequency to rated and set modulation to rated. This will give us rated voltage. And there goes the motor. Alright, and if we plot now, so we just do the capture. Okay, so now we have current. We can zoom in on that. You can see the current's actually fluctuating because there's a bit of an oscillation on the motor right now. That's because it's actually trying to run synchronously as a reluctance motor. This torque command actually isn't enabled right now. And there's the measured speed, and you can see it's actually oscillating. Turn the modulation index to 0, essentially shut the motor off. And then we can go ahead and turn the field on. Just turn field power on. Set it to maximum. And we'll actually have to exit from the GUI and rerun the GUI because the first initialization step in the GUI is to 0 the rotor position. So we'll exit and run the GUI again. And there you go, that movement there was the zeroing of the rotor. And now we can just click closed loop hysteresis current control. And again you can see the voltage. It's essentially looks kind of like PWM, but it is done by hysteresis current control. And we can see our 3 currents, phase A, phase B, phase C currents. That's the torque command again. It's not turned on right now, so the load is 0 on the motor right now. Commanded speed is 1800 RPM. and the measured speed is very close to 1800. There is a slight fluctuation in the reading due to measurement noise. We can basically take a look at the performance of the motor by using this alternate speed feature. So we'll go ahead and change this to 1200 RPM, and we'll enable alternate speed. So now the motor is basically switching between 1200 and 1800 RPM with a period of 2 seconds. You can go ahead and capture some results and look at the plots. Okay, so we can see phase A measured current. It's high whenever there's a transition. So this transition obviously is going from high speed, because of the higher frequency, to lower speed. And also we can see that the current at a certain point passes through 0 and then comes back up to keep the motor running. This is just a smoother version of that speed, and that's the commanded speed. So you can see that, of course, we can't track the instantaneous edge, but it's doing not too bad of a job. Over here we see the commanded Q-axis current, and we can see we're actually hitting saturation at the transitions. And there's the modulating signal. There's a feature built in called Tune, and it allows us to adjust the two control parameters, the proportional gain and the integral gain. So let's go ahead and try a different set of parameters here, 0.03 and 0.1. Just apply that. Let's take a look at our plot now. So we'll do another capture. Okay, so let's... Okay, so that looks quite a bit cleaner. It actually looks a little bit faster, very slightly, but the overshoot and undershoot is completely gone. Sorry, the overshoot is completely gone and the undershoot is completely gone. Alright, so I would say that's tuned about as good as it's going to get. Let's take a look at the smoother one. So you can see that's probably pretty close to critically damped. That's pretty good performance. And then we're going to change the load on the motor. And I basically have set up a signal generator to vary the torque periodically. And we're just going to turn that on now. So you can hear the pitch of the motor changing as the load changes. Alright, so we can see what's happening with the measured current. Whenever the load is on, we're drawing more current. When the load is off, we're drawing less current. And we can see that that's lined up perfectly with the torque command now. Recall the speed is set at rated right now, 1800 RPM. So there's the rotor speed measured. Sorry, let's go to the smoother one. So we can see that the performance is pretty good. There is, though, a slight overshoot when the load goes off, and a slight sag when the load goes on, but it does settle within about a quarter of a second to the actual commanded speed. And let's take a look at the Q-axis current, and you can see that the commanded current is tracking the torque command. And there's the modulating signal. No surprise there. Alright, so the performance is quite good. We'll go to 400 RPM and to rated speed. 400 is about the lowest speed that we can run at because the speed update from the rotary encoder is relatively slow. If we try to run lower than 400 RPM, basically the system will go unstable due to the delay in the speed calculation. So let's take a look at the results. The 400 to 1800 RPM. Okay. So we can see the performance is, let's take a look at the smoother curve. The performance is very good again. There's no overshoot. There's a slight undershoot here. That's starting to happen already because of the fairly large delay in speed readout already at the lower speed. A higher resolution encoder would solve this problem. Alright, one other thing I wanted to show is that we can basically save the output. We'll save this to a file named test. And It's basically a comma delimited file that we can open with Excel. And that shows us the performance of our motor drive. Alright, so very good performance at higher speeds, a very slight undershoot at lower speeds, and practically maximum acceleration. Basically, we're running into saturation and then running it at maximum peak current, 5 amps. I think that's about it for this demonstration. So we can just close down the motor drive, and when we close down the motor drive, it stops the motor. And we just have to make sure to turn the power off so we don't burn out the field winding. Thank you.